to our new shop. Um, just to give you some quick background, we specialize in lightweight sports cars, Lotuses in particular. So for us, performance is really all encompassing, right? But one of the most important things for us when it comes to performance is handling. Handling is one of those things that is often overlooked, right? We think, suspension's gotta be hard, it's gotta be stiff. No, actually, what you want is a suspension that's has grip, right? And grip comes from compliance. And compliance can actually give you some comfort, right? Where did I learn that? I learned that from my good friend Guy Evans. Okay. About 15, 18 years ago, we started doing business together. And he turned me on to triple adjustable shocks, which we put on our first Lotus race car that we raced in Lotus Cup. And we couldn't believe the compliance that we got. And so, anyhow, I'm here to present Guy Evans from Nitron Racing Systems in the UK. So their main headquarters is in Oxford, but they set up an operation here in Murrieta, just literally 5 miles away. And in fact, that white Exige right there, they've upgraded. It needed a rebuild of nitrons, and we took it from doubles to triples. We also needed a spring rate change, softened actually for more compliance. So anyhow, thanks for coming. Without further ado, let me introduce my good friend Guy Evans to talk to you guys about this film.
Thank you, Snoop.
All right, guys.
Yes, I've known Snoop for about 18 years, and so we've been working together. We've done 4 previous talks, a bit like this, around the place, over in Las Vegas and the racetrack and here in Temecula. And the knowing Snoop was really one of the reasons why I came here and why I'm here today. So if I just give you a little bit of background, a little bit of history. I've been working with race cars for about 40 years, exactly 40 years. Then we tested cars from maybe the age of 12, 10 or 12. And it's really led me on this path to working with suspension for the last 30 years, and then having my own company for 26 years. So Nitron's been in existence for 26 years. We have a headquarters, I call it headquarters in the UK, just outside Oxford. 38 people there, manufacturing, assembly. We have an assembly line in Japan, there's 7 people there, and copying the Japanese model of us sending the parts to Japan, where they're assembled by Japanese people in the Japanese market, which is 95% motorcycles in this case. We decided that we're really going to get into the American market properly by doing it ourselves. So I thought I would be the best person to set it up. And so I've come out here to really set the technical centre, to start employing employees. So Mike here, who's joined the company, we'll be employing more employees by the end of the year, and using really the American scenario of assembling the product here in America for the American market. This is the type of product we're talking about. Shock absorbers, specifically shocks, sometimes termed struts, coilovers, call them whatever you got. This is the product that we make, and this is why we're here. So Shanir said to me, lots of people don't really understand what suspension is, how it works, how important it is. And it got me thinking about a tagline that we had in our Japanese sales operation, which was respect your engine, fit nitro. People like, oh, what does that mean? It's really okay. It's fairly straightforward to bolt on a supercharger, add more power. If you're already struggling to use that power, adding more power doesn't help. If you have a car that handles okay and then you add more brakes, you can actually get worse. You can exaggerate the existing problems that you have. So suspension really is critically important to everything we do with our cars, how we use the car, whether we're going shopping, whether we're going to a racetrack. There's so many variations that used to be put a car to. When we go buy a car, they expect us to Honda to sort that all out for us. We get in the car, we can do whatever we want. So really, I'm going to talk a little bit about what it actually does. I'm going to talk about the suspension and exactly what suspension means. Then the very important part is the entire contact patch. That's what it all revolves around. the geometry of the car, dampers, what they are, how they work, and then really a lot of questions you're going to look at, how long do they last? How do I look after them? What do I need to do with them? And then we just finish up with kind of questions and conclusion. So thinking about Nitron, Nitron is effectively a design company, designs, manufactures prototypes, and fits shock absorbers, suspension bars, to cars, in this case cars, but also motorbikes. And then once the design is finished, we've signed it off, we've done our testing, we've got our customer satisfaction. You then subcontract manufacture these parts for local machine shops, specialists, while we get on with the next job. So we have in-house machining, we have in-house prototyping. This part here, for example, was a stub axle for an air-cooled Porsche. We get asked for this a lot. And so we'll turn this design from a 3D print, I'll pass it around, into a investment casting. So like the lost wax process using stainless steel. And then that will go into one of our stock products. And it's a long process. It'll take about 2 years to go from idea to saleable parts. So this is a 3D print part. And we use scanning, 3D printing, machining, casting. We use lots of different methods of ordering for production. Pass that around. So Nitron really does the design work. We're not a company that just screw shops together and it's up to you guys to sort it out. We do that job and we provide the whole package for you. So when you buy a kit for your Mustang, you get everything you need, all the bolts, all the brackets, any bolts you might need, it's all in the box. Here's another example of why we're here. You don't really have many Mustangs in the UK, we don't have GT350s, and we certainly don't have people that race. Didn't quite fit, needed some adjustments. Then we run stress analysis, where we stress the part on the computer to find out how it's going to fail. Then we make the final part, check that on the car. That works. Next step, machine it in metal, test it on the car, sign it off, goes in production. So these are kind of things we do. As a company. So being here really is giving us access to cars like that C8 over there. Not available in the UK in any form. People might import them. Somebody who wants a C8, they're not going to let us have a go. It's going to be their precious toy. So the only real solution is to come here, buy a C8, rip it apart, measure it, scan it, come up with some solutions for it. In this case, a specific bottom mounting that fits on the lower arm. It has to have this mounting, and there's a special top plate that goes on the top. 3D printed part and tested it on the car. You can support the weight of the car, we wouldn't drive it. And then that goes into production, and in 5 weeks' time we get our metal parts, arrive from the machine shop, and then we'll be able to do that as a solution. Once we've got the metal parts, we'll do the valving work to make sure it rides correctly, damps correctly, and then you guys are going to take it to the racetrack, on board across track, and you'll pull us up and say, hey, can you do this, can you do that, can you make it shorter, longer, different valve? That's why we're here. That's what Nitron does. So I moved down in January with my family, and I'm here to stay. Love America. I don't want to go back. It's England, raining, miserable, terrible food. Yeah. So when we think about suspension, what is suspension? What does it do? Why do we have it? Are there any vehicles that don't have suspension? So suspension really, in the word, it suspends the vehicle, whatever it is, whatever type of vehicle it is, tank, you name it, it suspends that vehicle above the ground and it isolates it to a certain degree to the undulations of the ground over which it will be traveling. So when you think about suspension, you think about springs. Yep, springs will do that suspension job. You take a body, you sit it on some springs, however many you need, and it sits on its wheels, the wheels contact the ground, and off you go. So we call the bit that's suspended by springs, we'll call that the sprung mass. So the sprung item sits on the unsprung item, which is the bit that's in touch with the ground. So on this card here, the unsprung items would be tire, wheel, brakes, calipers, the knuckle, I think you call it, above the bearings, parts of the suspension line. So these things are not suspended by the suspension. But all of this part is suspended. And so you've got the 4 springs and you fit it into your vehicle, it's the first one you've ever made, and you go off down the street. What's going to happen? Yeah, it's going to start oscillating. And it's going to start oscillating back. Because each corner is going to do its own thing in its own time, and it's going to do it with a different degree of frequency. And before you know it, within about 10 seconds, I guess, you're going to be starting to run. You'll crash. Impossible to drive a car with no shocks, no dampers. So this thing is oscillating away, bouncing away, and why is it doing that? It's doing that because the sprung mass is being pushed by the wheels through the springs each time it encounters any kind of undulation, whatever it is. And around here we've got these very high cambered roads which meet other roads with these big concrete drainage ditches. You go over those straight in a truck, but in something like the Corvette it's not so good. You've got to slow right down. These are big inputs that the chassis can have. So we need to control. So when you compress a spring, if I compressed it and said, here you are, you ready? You're going to be nervous getting hold of a compressed spring. You're going to think, I'm not sure I can control the spring because there's energy in the spring. So we're going to take a compressed spring and you're going to be very nervous to receive it due to the energy which wants to come out. So each time the suspension compresses, it puts energy into the spring. That energy is going to come out. And so when the spring compresses, you all know it will then decompress. In fact, it'll extend to its length before, and it'll overextend slightly because as it extends, it's pushing up the body, which weighs a few hundred pounds or a lot of 1,000 pounds, and that body is going to go up to its original length, and then its momentum is going to keep it traveling upwards. And then it's going to come down under gravity, and then it's going to go back up again because of spring energy. And this is the oscillation up to the right height point, over the right height point, back again, and that's why you go at it and solve without any form of damping. So the damping has 2 functions really. It's designed to slow all that down, but it's designed to take the energy from the spring, the energy and the mass of the body, and turn it into a different energy. I'm sure many of you will know, that energy cannot be created or destroyed, but you can change it from one energy to another. So what we're doing with a shock, with this kind of thing, we're saying there's all this energy in the spring, and each and every movement, energy is put into the spring. We take the energy out of the spring by slowing it down, not allowing it to just fire back up again, and turning it into heat energy. Hopefully, not noise energy, or you guys are going to complain. So we want to get the energy into the shock in the form of heat by heating up the oil from the shock. So, does everybody understand that shocks are full of oil? Yeah? What about a gas shock? Well, is it full of gas? No, all shocks have oil. All shocks have oil. Some of them have gas, some healthy oil. The shocks are primarily filled with oil, and they are taking the energy in the spring and turning it into heat inside that oil. Now, if you imagine you've got the car and it's got suspension and we attach some shock absorbers to the car, driving along, hey, this is much better now. I'm not oscillating and being shot on the road. So now we've got heat going into these shocks. The shocks need to get rid of that heat. They carry on building up. Just like brake fade, you'll get shock fade. And when you get shock fade, it's back to no shocks again. So we need to make sure that our shocks get rid of their heat easily. So if you go and take a cheap production car, or not so cheap, that's still not expensive, and you go take it on your track, if it's got its lowest type of shock absorbers on your car, then get to overheat. And after a while, you're going to think, hang on, this handling is going away somehow. I'm not much happy. So you need to think about making sure you've got the right product for the job. So thinking about suspension, the other part is really the contact patch. Suspension, yeah, we're controlling the vehicle. We're keeping it damped through our shock absorbers. So making sure it doesn't oscillate away and get away from us. We all know that feeling going over some big dip and it bounces and then it stops bouncing. That's the damp that's doing that. But the other part is geometry. If your wheels are pointing in all the wrong directions, even slightly, that car is going to feel horrific to drive. You'll feel like the car is driving you, you haven't let control it. And so
I want to ask a question.
yeah,
Tactical oil,
yeah.
is that primary reason for remote motors? The oil?
You only don't have a minute. Yeah.
Okay.
Yeah. Yeah. So when you think about the geometry of the wheels and the tires, they've got to be in the correct angle, vertical. They've got to be pointing in the correct direction. Now, suspension, when it moves, it doesn't have that wheel just go straight up and down. That wheel will be designed to move in a certain path or a certain direction, both upwards, and if you look down on the car, as it moves upwards, it's maybe going to move inwards slightly. What that does is the design of the car enables the tyre to retain grip on the ground. If you get your geometry wrong, as you load up a tyre and it's pointing in a different direction than the one you want to go, well then you've got a problem. You're going to have to put more steering input into it to try and get it to go where you want it to go. So the manufacturers design cars to do things in a certain way. So something like a Suburban needs to have very, very neutral suspension. It doesn't really impart anything into the car. Otherwise, you're going to start thinking about your driver. People who drive those cars, they just want to get to where they're going and start thinking about cooking or whatever it is they're doing. They don't want to think about the driving. The car needs to do that. Hence, it's the gearboxes, all these things do that job for us. So, with the suspension, what it's doing really is it's isolating the car. It's taking the energy out of the inputs, but it's also translating what you want as a driver into the car. Because you're going to brake, you're going to steer, any of those actions, the car is going to change its attitude. So when you brake, it's going to dive. When you go into a turn, it's going to roll. When you put the power on, it's going to swap. If it's got any power, it will swap. It's equivalent. They're not always good. So if you think about the suspension, it's doing all of that. You as a driver, you're in your bucket seat, you've got your harness on, you become part of the car, you're strapped in nice and tight, you're nice and light with the wheel, you're not grabbing on, white knuckle ride, you're allowing the car to find its grip. But this grip is coming from where? What are you feeling when you drive that car? When you brake, what are you feeling? You're feeling this thing over here. It's pretty small and it's called a contact patch. So the tyre's contact patch is really you, the tyre's contact patch and the road. It's all about that. Everything between your body, your senses, and the tyre contact patch is part of the system that the engineers work. And shocks and suspension are one of those parts. If you have a chassis flexi, some old cars with a flexi chassis, I've driven cars where you look down the hood, you can see it twisted, just driving along a normal road, like an old Austin Healey or something like that, horrendous. So modern cars, they're always stiff, like old cars. Some of them are really stiff. You can add a cage to make it even stiff. But having a stiff chassis is important, because then suspension can do its job with moving instead of bending the chassis. So a car like this, ultra stiff, very big tube frame, it's not going to twist, it's going to bend. So the suspension's going to do its job. So you, as a passenger, driver, you're feeling what the car's doing, and then you've got the contact patch. Now the contact patch, we talk about, we get some Hoosiers. It's great, nice sticky tyres, we've got some nice grippy we've got a tyre, asphalt. maybe you call it asphalt. You've got your nice grippy surface, you've got your nice grippy tyres. So when you brake, there's resistance put through that tyre, and that resistance through your brakes is slowing them harder. And if you brake too much, you overpower the grip that you've got, and you're going to slide. If you go around a turn too quickly, physics is physics. I don't care about modern tyres and things. Physics is physics. You go around the turn too quickly. Anybody that's raced will know that feeling of, I need to do something about this to stop it from sliding, or where I want to go isn't where the car's going to go. You need to correct it by unwinding some steering, maybe, or whatever you need to do, adjusting, modulating the power, modulating the brakes to get the car to go where you want it to go. And it's all because of these contact patches, these tyre contact patches. So the contact patch, let's say it's typically that big. So all that force is going through this tiny little rectangular rod contacting to the ground. Now, when you brake, you will all know that the grip that you get increases. So when you brake, the weight of the car goes down on those front tyres, and those tyres, you can feel it. They're doing their job. They're arresting the car. They're stopping the car. Those contact patches. Okay. They're getting bigger. The tyre is squashing. The weight of the car is squashing that tyre. And as it squashes and gets bigger, you can imagine there's more grip develops. We can agree on that? What about the rear tyres? Well, they're getting smaller. You know, you see motorcycles do stopping, so they go on the front wheel just by braking. So they're braking, they use their body weight as well. The contact patch on the rear tyre has actually gone to zero. It's off the ground. But there are times when the amateur rider doesn't necessarily know what's happening with the rear tyre. He hopes it's gripping, but he doesn't know it's gone really, really small at the point. And if he decided to apply rear brake at that time, what would happen? The rear's going to lock that. So, but at the front, he's able to pistols a brake and push a load of brake through the front. So, a motorcyclist has control of front and rear brakes. That's not going to happen. But you don't. You've got one brake pedal, and you're relying on the car to send it out. Well, you can't really do that. It's preset to have front brake bias and rear brake bias. And when you get it wrong, the ABS comes into play and says, actually, I need to release your braking grip on this particular tyre because I run out of grip. Now, we typically run out of grip because the contact match has changed in size. So front ones, more and more braking, bigger contact patch, lots of grip. Rear contact patch, oh shit, it's actually now getting really, really small. If the car can't adjust its brake pressure. One brake pedal, one master cylinder, two lots of brake pressure going down. So what we need to do is think about how does the car deal with that? It deals with that with good dampers. So dampers will change and control, this is a critical thing, the contact patch load. And our job as engineers is really to make sure the load change is minimal. So we call that contact patch load variation. We want that variation to remain as constant as possible, minimal variation. So if you imagine going around a bumpy turn and you get that feeling of, I've got grip, I haven't got grip, I've got grip, I haven't got grip, I've got grip, I haven't got grip. As a driver, you're going to go, oh, I'm backing it all off here, this is sketchy, I'm not happy with that. Why? Because the contact patch gives you grip, then you perhaps go over a bit of a dip in the road, and suddenly that contact patch has gone small. But the sideways load on the car, you've given it, it's constant. And therefore, when you've got grip, no problem. Grip, sideways load, you're in control. Next fraction of a second, the contact patch has got smaller. Suddenly you've got no grip. The car starts to wander out. Your feeling is not happy. Then you get into the next compression. Oh, I got grip again. And then no grip. And you don't like, I don't like the nobody understand. So what we need to do is think that the damper's job is to really control that and make sure that variation is kept to a minimum. And if the variation is kept to a minimum, everybody's happy. Everybody goes, oh, this car's a nice car to drive. Now there are some really sophisticated systems out there now. Newer cars are coming out, dampers adjusting all the time, electronic ones, like this. Plug it in, and then there is a valve, electronic valve, and it goes, okay, every 6 thousandths of a second I'm adjusting myself depending on the conditions that I'm seeing on the car. And there are electronic boxes that sense what's going on, and they adjust parameters on your car. Whilst on the steering, and they adjust down. And so things are really moving on in the last few years, quite a pace, but the newer supercars are coming out, and the drivers are just astonished. How on earth does this car grip so well, feels so neutral, feels so easy to drive quickly, and it does it through clever electronics. But let's think about one-tap max for controlling the dampers, but what's in a damper? You know, what's in these things? I mean, they all look pretty similar. You can go into the shop and buy something that looks like a shop. So I'll take those in my Forerunner. What's inside it? You don't really know. Something is magic.
Say again? Magic.
Magic, yeah. So we talked about the different types of shock. You know, we've got gas shocks, oil shocks, or what's in the shock. So I sort of prepared this little more just to give you a brief understanding of what's inside the shock. There are two principal types of shocks. You've got a shock, and all of these here are what we call shocks. Whether it's got a vent, or vent shock, the vent bolts for the car, the suspension arm moves up and down. It's rotating on its bearings for the bearing gear, but principally it's a shock. It's got no structure to it, you can bend it. It's just a shock. And then there are other cars out there like BMW, and on the front it's got something called a strut. And the strut is a great big heavy structural part of the car. So here we can see we've got shock in a suspension system. This is the body of the car that's strung, it's going up and down. There's your tyre, wheel, this is your knuckle, and as the body goes up and down, these suspension arms do that, and the shock opens and closes all over. Simple. And it can be light. And all it's got to do is absorb the energy in spring, turning the heat, and if the shock snaps, the wheels don't go forward. The wheels are held with a suspension arms. And then you have a strut. Near the strut, the car itself, moving up and down. Wheel, the knuckle, but attached to the knuckle is the strut. That strut forms part of the car. If that breaks, the wheel falls over, crash. So struts are very different. They're heavy, they're even with steel, you have a great big shaft on them, and they are part of the bending resistance in the car. So when you're doing 140 down the straight, some cracks, you bury that pedal in, you can hardly breathe when you're braking it, but that wheel brake resisting the car from wanting to go straight on is trying to snap that. So let's do it. And if that does snap, tend, foam, brake, you're in trouble. So the struts that we make haven't got any gear. They are designed to resist the most extreme forces you won't put into them. You want to go to the table racing, Nürburgring, run through the carousel, go over all the curbs, and just be professional drivers in the car that actually just want to win, and they don't really think about the fragility of the parts. They trust the engineers that make them strong enough. We've got to make parts that can withstand all of that, and we can win. We win championships in races with shocks and struts. So these are the two principal parts. Now when you think about the shock itself, the principles, there are really two types of part. There's a twin tube and a monotube. So I draw them so it's the same layout in the car. You've got top eye, bottom eye, opening and closing, and this thing here. With an eyelet on the top, eyelet on the bottom, it can be rubber, it can be a bearing. So there's two eyes. Sometimes it's a thing, going through a rubber block. Got the shafts, and inside is a piston. And the piston is moving up and down inside oil. Both types of product. You can add a bit of a magna ride yourself, where you've got your piston running up and down the side, magnetic fluid. You can have an old-fashioned shop that's fitted to an early 60s car, something like that. But at the end of the day, they're all filled with oil. The oil is the medium that absorbs the heat. And as shop manufacturers, we're lucky because oil technology has improved. In the last 20 years, shop oil has really improved with synthetic oils that will stay stable under extreme conditions. We've got a trophy truck. We've almost looked at trophy truck and thought, what is going on there? What on earth do those shots go for? Absolutely destroyed. But with good fluids, they can take all that energy from the trophy truck, they can turn it into heat in the oil, and then it can dissipate that heat using a thin shocks, using heat sinks, using reservoirs. Give it more oil. Let's add a great big reservoir of oil. Let's pump loads of oil around the system. Gives it more oil. And the reservoirs can have fins on them as well. Just get rid of that again. Just trying to get rid of that energy so we can absorb the next impact and the next impact and the next impact. But ultimately, they're going to be something like this, fitted to the trophy truck, fitted to the Lotus Victoria track game, fitted to the Formula One car. But these, they all do. So how do they work? What goes on? So there's two principal movements: compression, with one pump, rebound, when you fill it open. There's only two directions of fills. So let's take this product here to start. I was making this. Twin tube shop. You've got one tube when you look at it, and inside the shop there's a secondary tube. And inside that secondary tube there is a piston running up and down inside that tube. And as it runs up and down inside it, oil that is above and below it has to pass through. And to get from one side of the piston to the other, there's a piston child that will hang around. There are little tiny shims and plates covering the holes that the fluid has to pass through. So the oil wants to go from here, here. So you're pushing this rod in. As you push the rod in, piston goes down, and all this oil here wants to go through to the other side of that piston. What it does is it bends these little tiny shims out of the way, and the action of bending it requires energy, requires force. That's the point at which the energy is taken out of the spring and put into the oil. Because the oil meets that shim that's covering that hole, meets that shim and goes, okay, I'm going to have to push you out of the way. But the shim is a spring, it doesn't want to be pushed out of the way. It will be pushed out of the way. And as it does that, the oil, the chain molecules in the oil, they get sheared. And the shearing action before they rejoin on the other side is the energy. Shearing those chains required energy. The spring loses energy and the oil gets hot. It's just literally a direct transfer of energy. It's an energy converter. Once this piston moved down, it's down here somewhere, oil is above it, and then rebound occurs, pulls it back up again. Now all this oil above the piston is got to go back down again. And up again and down again, and up again and down again. Sometimes it's doing it in tiny movements. You know, when we film these cars, we film the shots, we see the shots are moving like that, and then they have bigger movements. They're always moving. They're always doing something. Whenever you drive anywhere, the shop is moving all the time. Sometimes big, broken truck, sometimes smaller tractor, but they're always moving. They're always passing oil up to them. Now, when this rod goes in, and you have a chamber, if I took this and I said, okay, it's full of oil, up to the top. If I put my finger in the top, what's going to happen? Oil's going to come out. So if that was sealed off with one of these things, and I went to try and put my finger in and there's no way for the oil to come out, I couldn't put it in. So there must be something inside a shop that can squash to allow this rod to come in. If this thing is completely full of oil, you can't put anything in it. So if I put my finger in there and there was something squashy inside, like a miniature bag of chips. Imagine a miniature bag of chips full of air, inside there, completely surrounded by oil. I put my finger in, that little bag of chips is going to squash up. Yeah, I agree on that? So you don't want to do that. Some shop companies do. They put in here, in this gap, between this tube and this tube, they put a little bag of chips, a little tiny bag, right? And that compresses when the rod goes. Other companies, they just leave enough air in the shop when they make it, which is your normal production car, the Suburban. It's got just an amount of air in the shop that allows the rod to go in. And they hope that the air is going to go, well, they know it's going to go to the top of the shop and it's going to find its way to the gap between those two tubes. So this part here is full of air. Or if they're a better quality shop, they'll inject nitrogen into the shop, which is more inert, to have moisture in it, to change volume to as much as air does. But this space running around these two tubes allows the rod to go in. That space there, that air will squash up by the amount of rod that you put. So that allows the thing to go in and out. So we've got a cylinder with 80% full of oil, and there's 20% full of air, nitrogen, something like that. But these two can mix. So if you start getting a bit fruity with your car, then you're going to start getting air mixing with your oil. And it's going to emulsify, and you're going to get this fluffy mixture in your shop, which I'm sure you can guess by now is not really ideal. You don't want to get that popular stuff, but again, it's fade out. Car starts to lose control, the other things too hot, the works are too hot. So we need to really keep these items separated. Hence this packet, the chip packet idea was completely separated, but it doesn't really work out well. But this is a twin tube system. Now, a gas water tube system only has one tube. So most people have heard of Bilstein. Bilstein really, they took the principle by a French guy called Carbon, and they turned it into a production system. So you'll see some cars running around with Bilstein badge on the back, Subarus, things like that. They've got a system like this, but Bilstein only make the gas monotube system. The gas monotube system, very simple. One tube, mono tube. The rod comes in. Allow this rod in. You're getting this gas part here squashed by the same amount. More rod in, that would squash more or less. And there's a little disc that sits between the oil and the gas. And that disc has got seals, it's got a bearing around the outside. So that disc runs up and down as the rod goes in and out. Not very much. The volume here isn't much moving down here. So gas monotube separates the oil from the gas. Doesn't matter how hard you work here, you're not going to get gas emulsifying and mixing with the oil. It's going to keep it contained with solid oil. Now that's good from an energy absorption point of view because it keeps that oil solid. It's able to absorb a lot more energy than a frothy emulsified oil. Same idea as here, but notice the piston size is bigger. Now the bigger the piston, the more control you have. So if you imagine you've got an area of oil and you're pushing a piston through up and down, if you have an inch of motion with a little tiny half-inch piston, it's not really a lot of oil you're using in that motion. If you've got a big 2-inch piston, with the same motion, you're using a lot more oil. So you're actually able to put the energy into a larger volume of oil. So again, another benefit. You've got more control. If you have a movement that is only 1/16 of an inch up and down, then with this system here, you're really not using very much oil. So the same oil is being used again and again and again and again. If you've got a bigger piston, more oil, you're spreading that energy amongst more oil. It's a better way to do it. So gas monotubes really are the way to go if you've got a performance. So is that really clear how they work inside? Any questions on the way they function? So I've got some more parts here I'm handing around. This part here has got all the seals and bearings in, and you can see how that works. So another one there, bearings.
Yeah, circular monitoring.
Yeah. So now
going to change in there.
Yeah. So now we get into how they change, how do they vary? What's a remote reservoir? What are all these other bits and pieces? What's an adjuster? Okay, so there's your basic shock layout. You've got water tube, you've got the twin tube. Yes. How would we vary the damping inside this thing? What would we do? You've seen shocks that have a knob on them. Okay, there's an adjuster knob. What does it do?
Bring the plates.
Okay, so what they nearly always do, is they take it with oil, it's going through the piston, it's pushing those shims I talked about out of the way, so the oil's got to get from one side to another, it's got to bend those shims. So let's give it a little bit of a cheat route. Let's give it a hole that goes down through the middle. Tiny hole. So some oil can go around those shims. It's given an easier path. That you as a user can adjust that hole. Let's say going and close it off, and you get stiff down. If you can open that hole right out, it's a needle of jet principle. So literally there's a jet, and there's a needle that goes in it. And it's all inside there. So the oil will come down past that needle, get to the other side of the piston without going via the shims. Now you can make the needle and jet or open or close with the adjusting knob, and you get harder and softer damping. Says you cover it. Same as a car, yeah, very good. Sense cover. So that needle and jet you've got control over. Now if we look at this electronic shock here, how does that work? It's the same idea. It's not a needle and jet, it's a solenoid coil. And the solenoid coil is opening and closing a little tiny barrel system. It's got more or less little openings in it, depending on how far you open it. So you use electric current, 5 volts, to open this thing fully with 1.6 amps, fully open, 0 amps, it's closed. And depending on what current you put in, and that depends on really what this guy says. Right, okay, now put in 0.72 amps, it's going to move to a particular position, it's going to open so many holes. So this type of product, future really, if I'm honest, allows pretty much infinite control, depending on how many decimal places you want to put your current controller, to move the with which the oil can move around those shims, how big that dam is. And if it can change it every 6 milliseconds, from full hard to full soft in 6 milliseconds. Literally, it's like full hard on the damping to full soft, it's the same unit of calibration. You've got incredible control. So then that's down to how clever are your sensors in the car, how clever are your algorithms, how clever are the engineers, how much time do they have to set the car? 5,000 hours or 15,000 hours, because it's that much time is needed to set a car. So the oil moving around in this, through the shims or around the shims, dictates how hard or soft your damper is with those shim settings. But if you take that damper from this car and you go and put it on an Aston Martin, it's not going to feel right. So then the engineer will go, okay, I need either a different piston or different shims or just different shims. And they've got a whole range of options they can use to tune the dampers to go, right, I'm gonna put this kind of damping setting. And we have dynamometers that open and close the shocks on a program and then read the force that the shock generates. And you've got 2 of these dynos up in the workshop in the reactor. And then we'll read the pulse on the shock and they'll give us a graph. And then the next cycle down the dyno can actually replay scenarios. So back in Oxford we have an electromagnetic dyno, like a hovering train, magnetic train. A whole cartridge assembly that holds the shock is magnetically suspended, and we can grind it up and down on magnets, and we can replay a lap of the track. You can see what the damper is doing, how much does it move, what's happening to the shock. We can record a temperature gain over one lap of the track. You can see if there are any issues anywhere. Is it going onto the bump stop too much, too often? Do we need to tune the length of the pump? So we can do all that sort of stuff. So hopefully this is giving you an insight into the way in which we work, what we do, what we're making, how the dampers function, how they adjust. Reservoirs really give you another form of control, because you can put a hole out of there and allow the oil to go into another compartment, and you can change the compression as the oil comes out, and then you can allow it to free flow. You can change the compression and the rebound speeds independently. That's why we use oil. So, but I think right now it's fully enough to embed it to grips. Any questions on what we talked about? Anything to think about?
So the adjustment in bump and rebound makes sense. What's the third triple adjustment?
Okay, so when we think about high speed and low speed movements of the car, we think about the low speed movement is when you're applying the gas. So you're on the gas and the car is squatting down. That's a lower speed movement. You're controlling it. A high speed movement is running over the curves. So if you had a controller that would allow you to adjust how it was affected by curves, how the car felt over the curves, and then you had another separate adjuster screw that allowed you to adjust the feeling when you applied power, because it's England, it's raining, or it's California, it's not raining. You've got differences. You can isolate the movements, isolate the speeds, and go, right, this is affecting the low speed. So this knob here, low speed controller, was affecting how the car feels on the back, on the front, how it feels under braking as you feather out your braking and you're in turn. Whereas the high speed movement, you try and set it up with the bumps, and raining or not, England or America, a bump is bump. But you can't affect that while you're driving, you can go over and you don't. But it's really giving you that feeling of, I can isolate bump control, and then I can isolate the grip control. So think of it as a grip string. So that's where you would have a high speed and a low speed control. In rebound, it's not that important, because if you imagine you run over a bump, it can be really fast. If you hit a curve, it can be really high speed. But the rebound was very limited. It's really the energy in that spring and the weight of that unsprung mass pulling it down the road. And so you can have a really very high speed compression movement, but actually quite a low speed rebound movement. It's not going to be that fast. Because what could pull the shock open as fast as you compress it when you hit it? Okay. So having a high speed, low speed rebound is not as critical, not important really, compared to high speed, low speed compression. Because so that's the Shelley talks about the three ways: high speed, low speed. Here's your low speed. That's adjusting your grip for the day, or the difference between Spring Mountain and Upper Willow, different track surfaces, different temperature. You might think I've got less grip, more grip. You can adjust it on that. Whereas the compliance going over the obstacle, over a curve, that's the same. That hasn't changed. Hot or cold, wet or dry, that's the same. So you'd set that, then you'd independently set that for the day. You might set it throughout the day. Conditions might change. So that's why you have a high speed, low speed compression test.
When you see a car exiting a turn, performance car in the speed and the front end, linear, that you typically down.
Okay, so you've got a car, you go through a turn, and you're lifting an inside front wheel. Now, it's known amongst engineers that the grip from two tyres is always more than the grip from one tyre. Always. However, there are circumstances where you don't actually need any more front grip at that time. So you will get circumstances, notices do it, where as you're exiting to momentarily one wheel will hang in the air. You didn't really want even more grip. You've got enough grip, the car is balanced. And that could be either a function of momentarily, the car is lifted and the rebound is so stiff that the tyre hasn't come down yet, or it could be set up so there isn't really much grip on the car at that point.
But sway bar.
Yeah, sway bars really, you think about a sway bar as a diagonal load transfer bus. Sway bars, yes, they act across an axle, but really you use the sway bar to diagonally from diagonal switch axis to control that. But the sway bar, if it's one of those solid axle conversion hits, it'll lift up a front wheel. If you compress one, the other one will come up. If the spring is light and the mass of the rear tyre is light, yes, it can lift it up. But I would say normally I'd want to set a car up to try to keep all four wheels in touch with the ground all the time. And I try and do that. But there are circumstances where you don't need more front grip in that case, and then you'll allow it and say it's not important, we'll let that go.
Because part of it, I can see pictures of my car making a turn. It's extremely rare. I have here.
Yeah.
And yet I see a lot of others. I'm like, no trying to shoot it back.
Two tyres generate more grip than one tyre. That's just physics. Okay. Definitely. So the more even you can spread your load distribution between two tyres, the more lateral grip on that axis, that axle you'll generate. That's just fact. So the more weight you put on the tyres, the more grip you generate. Hence your big front your big wing, and you're trying to push down on the car without making the car negative. That's error.
Okay, tell us why and how shocks wear out, why they need to
Servicing, we didn't do that. Okay. So you've got a bunch of fancy shocks, and you put them on your car, and you're thinking, servicing. I need to get any service. When, how often? Okay. There's no fixed formula that you can apply. What I can say is that the moment you start using that shock, it's degenerate. Very first time you use it, we put it on the dyno, it's degenerate. And absolutely brand new as we spec it. The oil, we talked about breaking the shock molecules in the oil, and those molecules, breaking them is effectively degrading the oil. You can only do it so much. You open an old damper up and you've got like water coming out, horrendously smelling brown water. It has no damping functional ability at all. You can't absorb any energy. So I would say, as a rule of thumb, if you use your car spiritedly on the road, the weekend driving, and you took it to the track 2 times a year, I'd rebuild it after 2 years to keep it optimal. Those shocks that we had in recently, they hadn't seen the light of day or rebuilt for, I don't know, 15 years, something like that. So when we opened them up, a whole load of mud came out, which is just oil broken down, sits on the bottom of the shop, and you just clogs up all the orifices, it stops the thing working. So that the person who's driving that car must have been riding for a long time non-functioning shocks. But I'd say every couple of years you want to keep it absolutely optimal. If you do hard track days really they punish the shocks more than racing. Because racing might be 20 minutes or an hour. You know, hard open track days with a fit driver, they could be out there for hours. You do that many weekends a year, at the end of the year, you absolutely need to get the shocks filled up. Now, when we rebuild them, we'll change the oil out. That's the number one thing we'll do. We'll change those shins. They're the things that bend and take all the energy. So the shins and the oil get changed, and then we'll change the bushes, the seals. We'll take apart the adjustment mechanism, clean it out, we'll re-grease it. We'll check the bearings. We'll check the board for wear. We'll check the wood for damage. But really, it's the seals, the O-rings, the oil and shins are what we change. We'll run back up on the dyno. The check it's back to full health again. Every shop has got its own serial number. We'll record it. We'll put it in the book, the digital book, that we've done this work, and you get back a refresh shop. And that's what we'll do under your service and over. Any other questions?
How do you do adjustable right eye?
Just the right thing. So when you get your regular car, like a Corvette, you can't adjust the right way. So you go buy yourself, and the Corvette shop looks pretty much like this. You buy yourself an aftermarket shop, and then have a collar on it usually, allowing you to lower the car. Now, is that a good thing? Should you guys be lowering your car? So we work with Lotus as a company. Nitron works for the Lotus factory, and we were supplying the higher end cars, about half of their production, with shocks on the production line, and they were adjustable. They look like that. But when the new Amira came out, we got hold of one very early on, one of the first cars, and we lowered the car about an inch, and then we fitted the control unit, and we fitted solenoid shocks, and we went to Lotus for them to evaluate the car. And they said, "You've ruined the car, you've lowered it." And the engineers were really adamant that and you took it out on me, you destroyed the handling of this car. The problem is, it looked like you could put a family of squirrels under the wheels. There's just this huge gap. Nobody likes that. But it is a fact that if you do lower the car, you're lowering the mass. And you've got this whole idea of, you've got a London double-decker bus, can't go around turns very quickly because it will fall over. Why will it fall over? It's got a narrow wheelbase, and it's got a high centre of mass. Take it around a turn and it'll just tip over. So you can put wide wheels and tyres on your car, you can put space, you can widthen the track of the car, and you can lower the mass, and Visit says it can go around a turn quicker. It won't roll so much. You're evening out the pressure on the tyres more, they're wider. Therefore, you've got a faster car. So lowering a car using platforms is a good idea, but once you've done that, you absolutely must put on the geo grid. You must get the wheels pointing back to where they should be. Then you're halfway back to where you were. These things will change. If you lower the car, the roll centers and the geometry of the car will change. But just from experience, I'd say no harm done. I'd lower the car.
And what about the system where you don't want to straighten the node?
Okay, front axle lift.
Yeah.
Okay, so front axle lift, I didn't bring one, we did do it. The front axle lift is a kind of like donut shaped thing that sits around the shop, and in its normal condition, it's closed. It then has a system that allows you to raise the nose of the car by pumping oil into that cylinder. When you pump oil into the cylinder, it grows, eventually lengthens, and that pushes the spring up. On top of the spring is attached the part, and your car just goes up on the track. Now usually, if you look at that Corvette, it's got serious nose issue. It doesn't have an issue at the back. So normally you don't have front axle lift, you don't have a rear axle. It's normal. So you have front axle lift. They're standard on many high-performance cars. So they've got a low nose and a long nose. Especially Porsches, they have a very, very high overhang on the front, long nose. And so that front axle lift is something where you negotiate your entrance to your parking, or to a gas station, something like that. Push the button, the hydraulic pump pumps oil into that cylinder around the shop, lifts it up. Depending on the system, it'll self go down, or you've got to lower it yourself, depending on the system, and then you're back to normal again. And once it's closed, it has no effect on the car whatsoever. You're back to the same as if you don't have it. You know, you can put all the balls and all, you go do your track day with it, it's no issue at all. But it's a useful thing on a lower car, and they can be retrofitted. As long as there's room for the cylinder. That's the important part. If there's no room for the cylinder, springs too long, yeah. So we've done the mirror, we've put it into the mirror, that works well.
So two questions. One about the Nero, but we'll come back to that. But so when you're designing the shop and the valving system and the like, I'm assuming you're assuming a certain mass of unsprung weight as well, in terms of the wheel, valve, etc.
Yes.
Do your design parameters change much if you with lightweight wheels and you have to weight at the wheel, or does it not make that much difference?
Okay, so that's a good question. There is a general accepted percentage that you're looking at the sprung mass on the corner of a car to be at least 5 times the unsprung mass. That's pretty much a ratio we look for in the minimum. Some cars, that is a challenge. Something like a Nitron, if you know what a Nitron is.
Yeah.
It's a real challenge on some of those lightweight aluminium engine cases to get the mass of the sprung mass light enough compared to the wheels and the tyres and the unsprung mass. So you have to go to extraordinary length and magnesium wheels and things like that to try to get the unsprung mass lighter. Something like a Rolls Royce, they actually spend a lot of money, time and energy in getting the unsprung mass quite light, because the right quality is dictated by having a heavy sprung mass and a light unsprung mass. Right quality in engagement is question.
Not bad.
So I would say if you've got a car and you adjust the unstrung mass, I think you have to adjust it significantly to warrant change in valving in shocks or something like that. There are carbon wheels out now that are truly light. You know, you're eating something like the 350 Mustang, that wheel is light. It's really light. It's fragile, but it's light. And along with ceramic brakes, they're managing to get the mass, the unsprung part, really very light these days. Surprisingly, the difference between a racing tyre and a road tyre, significantly different in mass. And that mass is rotating, so again, it's important. So true race tyres, go to Le Mans, true race tyres, they're a special beast to the standard speeds they do, but to remain light. But certainly the valving should take account of the unsprung mass and the sprung mass, providing a solution that isn't too stiff, too soft for its setting. So yeah, somebody said I've significantly modified my car, I'd maybe look at the damping myself.
Yeah, actually, I had a Caterham with 15-inch wheels and then 13-inch wheels. It was way more compliant on 13. And it was actually it was a nice,
You also had high profile tyres.
Yeah, don't see that one.
That's Formula One used to have 13-inch rims, and the rated balloon tyres, very compliant. All the suspension was in the tyre. Now look at the Formula One cars, and they've got, I don't know what they are, they're large wheels, 18, large wheels, skinny tyres, massive challenge for the engineers to damp that and give what is effectively an ultra-light sprung mass some form of compliance, and then you see what happens when it doesn't have any compliance. It doesn't work. So you bring back the balloon tyre.
Pirelli wouldn't do.
I said if they need to stay in, if they had to come to something that looked more like what they could sell.
I guess.
So is there some, just quick days, there's something screwy about the Ackerman on the mirror that has to be at that right height? Is it?
You've got a lot of bobbins looking at drawings like that, designing their roll centers, designing their roll mass couples, designing their front and rear heat axis. They're doing all of that. And then somebody like me comes along and lowers it. But oh my God, what have you done to my baby? You've ruined it. Haven't you? But in their mind, they don't necessarily care as engineers about the arch gap around the ring.
They make that statement before or after they broke.
Well, they did try again and they said, oh, you're still ruined. I think I'm just entrenched that I'm ruined. But they were reluctantly impressed with the change in dynamic. Because everybody these days wants a car, you can go shopping in, you can even go to the track day and buy a car. You don't want to arrive track day absolutely broken through your journey there. You want to have a nice compliant car, get to the track day, turn the rotary knob, this thing goes, okay, you've arrived at the track, I'll put my track settings on and then off you go. It's important that we understand as engineers how to make the car compliant enough. But when you start pressing on, the car behaves as you expect it to do by respecting that contact pattern of variation, keeping that to a minimum. And on the track, we're putting in a lot more force. So, well, I hope you found it useful and a small insight into that thing. And I apologise if I waffle on certain things. It's I love what I do. It's not a job. Any questions you got afterwards, come and ask me. And
I had a question with the shock stiffness and matching the spring rate stiffness in the car and the correct shocks to put with that to match that spring rate. If they're not equal, then you again have a problem. So trying to find that correct balance between the spring rate and shock is difficult.
It is difficult, and it's really the engineer's job. If you say you've got a particular spring fitted to a car, we would have a good idea of what kind of damping characteristic to give it to damp that type of spring.
But the spring itself may be incorrect in the car.
Well, we can't help you with that.
Well, sure, you take the spring and just change that blue one to a black one.
But one driver and another driver, they prefer different things. You know, I've worked with a car that's got 3 drivers in the endurance race.
Yeah.
And you've got to try and compromise, because one guy likes it loose, one guy doesn't. They're all different. And so it's always a compromise. You can work with one driver with one car, and you can hone in what they like. And then if suddenly the teammate has to drive that car, well, I don't like this, I don't like the heading, it's too much travel. We find people have a subjective view of suspension, particularly, and you rarely get 2 people who like the same thing. So I could set your car up and go, like, that's as good as I like it, it's as good as I can get it. You'll get in and you'll go, what have you done to my car?
Yeah.
It is subjective.
Well, as an example, I have 2 Z06s, the 08 transverse spring, and that's the F4, the heaviest spring they have. They have 4 springs. But I also have the C7 Z06. Now was thought to be a street cruiser, but it will pound your kidneys out because it's a Z06, heavy springs. And I'm thinking it's not the shocks that are doing this, and they're adjustable shocks. You set it on the lowest, you set it on the highest, you get no right difference. It pounds your kidneys out. And so it's got to be the spring.
You'd have to look at that car in its individual case. You'd have to have somebody driving it and make an assessment of it. It's not what we think it is. We often find that we make some changes, we land up making something different that we didn't imagine we were going to make different in the first place. Each car and its architecture, you need to look at it.
You know, the implications of those changes to help guide you, right? And I mean, and also really to Guy's point earlier, you can have engineers theoretically coming up with a design and saying, hey, here's the perfect design. But then you hire guys like those two over there who are ride and handling engineers, and they get in and give their subjective evaluations to go along with that, because they're going to find that there may be something that subjectively is working differently than the theoretical. You see? So anyhow, so I think with that, maybe we'll draw this seminar to a close. We had, we started off at suspension 101, but I think we got the suspension 201. So hopefully that was, satisfying for you guys. I mean, Guy, thank you so much.
No problem.
You'll be here afterwards, so we certainly take, a lot more questions that you might have. All right. Thank you guys for coming.